Okay, so in this portion we are going to see how to project a vector v onto a subspace S. And let's imagine that both of this vector and this subspace both belong to the vector space V. So Vs is a subspace of V, and the small vector v, small v, belongs to this vector space V. So we are going to see how to project this vector onto this subspace. Now, how do we define a vector space? We define a vector space using its basis, right? One of its bases. So let's say we have the basis of this space. Let's call it B. So B is a set of vectors. Let's call it B1, B2, dot 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 Bn, which means S is an n-dimensional subspace. Anyway, so we are going to see two cases. Number one, when this basis is an orthogonal basis. Orthogonal basis. So what exactly is an orthogonal basis? It's pretty simple. When each vectors of a basis are perpendicular to each other, so B1 is going to be perpendicular to all the other vectors, B2 is going to be perpendicular to B1, B3, B4, all the other vectors. So every vector is perpendicular to every vector L, all the other vectors. If that happens, we call that an orthogonal basis. And number two, in the case of non-orthogonal basis, right? Non-orthogonal basis. Okay, so a very familiar example of orthogonal basis is the standard basis. So for a three-dimensional space, for R3, we have I hat, J hat, and K hat, right? I hat, J hat, K hat. I think I wrote the orientation on the other way. Anyway, it doesn't matter. So I hat is perpendicular to J hat and K hat. So each vector, each basis here is perpendicular to other two. So this is a good example of orthogonal basis. You are going to learn more about them in the next week. And in the next week, you are also going to learn how, if we have a non-orthogonal basis, how to convert it into an orthogonal basis. Those are the topics of the next week. So not going to get into that now. Anyway, so we are talking about orthogonal and non-orthogonal basis. These are the two cases. So we are going to see how to project a vector v onto a subspace S when we have an orthogonal basis for that subspace, and when we don't have an orthogonal basis, we have a non-orthogonal basis for that subspace. So these are the two cases. Okay, so case 1, we have a vector v, we have the subspace S, and we have an orthogonal basis for that subspace. Let's call this B1 up to Bn, right? Okay, so the project what we're trying to do, we are trying to find the projection of vector v onto the subspace S. This is just going to be projection of vector v onto the basis B1 plus projection of vector v onto the basis B2 plus dot 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 all the way up to projection of vector v onto the basis Bn. Alright, so we know how to do that. This is a projection of a vector onto another vector. Both of those vectors are inside the same vector space. We know how to do that. We learned that in our last chapter, or in our last part of this lecture. So we know how to do this. So when the vectors of our basis are orthogonal, this applies. How do we know that this applies? There is a proof. If you want that proof, please knock me on Slack. This video is getting long, so I'm not going to include that in our main video. I will try to create an appendix for this proof, or you can find the proof in the textbook. So I think that's better. Find the proof on the textbook. Anyway, so this is the easy problem when the basis we have is orthogonal. So all the vectors b1, b2, b3, bn all are perpendicular to each other. In that case, the projection is just this, right? So for example, you have like a vector 2, 3, 1. You want to project this vector on a two-dimensional space, the space which is spanned by 1, 0, 1, and let's say 0, 1, 0. I am assuming these two vectors are perpendicular to each other. I'm not really sure, and I don't think they're perpendicular to each other. 1 0 1, or probably they are, yeah, they are perpendicular to each other. So if you try to project this vector on the space spanned by these two vectors, you project this vector on this vector plus you project this vector on this vector, so that is your result. Okay, so let's move on to case 2. All right, case 2, we have again a vector v, we have a subspace and a basis for that subspace. Just like before, we have b1 all the way up to bn, but this time these vectors, as they are the basis, they are linearly independent, but they do not form an orthogonal basis. So b1 is not necessarily perpendicular to b2 through bn. Okay, so side note here, if you have, instead of a basis, if you have a set of vectors, let's say b1 to bn plus 10, let's say, which span the space S, but they are not the basis, which means if it is an n-dimensional subspace, so clearly we have 10 extra vectors, which means these are not linearly independent. In that case, you can just use elimination to find which of these columns or which of these vectors are independent and keep those n vectors to form a basis. If you have redundancy, just get rid of one of the redundant vectors. All right. Okay, side note over. Let's get this erased. Okay, where were we? All right. So let's form a matrix with these vectors. So we are going to call this matrix A, which have the columns. First column is going to be b1, this is a column. Second column is going to be b2. So we have bn, we have a matrix, and the subspace is the column space of this matrix, because the column space is the span of these vectors and this is the basis of S. So S is equal to column space of A. Now we are going to try to project V onto S. So let's try to draw some figure. This is V. So we have, let's say we have a vector space. This is S. V does not belong to S, because if V was a member of S, the projection of V would be itself. Now we want to try to find this. This is the P vector, that is the projection of V onto S, such that this is minimized, the error. And this is going to be minimized when this is perpendicular to this vector space. Now this is easy to draw when we are talking about two-dimensional and three-dimensional stuff, but this applies to any dimension, any higher dimension. Okay, so as you can see, this E vector, just like before, just as we saw before, this is just a higher dimensional extension. This E vector is just V minus P, right? From V vector, we are getting rid of the portion that reside inside the subspace. We get the portion that is perpendicular to the subspace. P is inside S, E is perpendicular to S, just like we saw before. Cool. Okay, so we are going to net this here. So notice the vector E, this vector is perpendicular to everything that is inside S, which means this vector is perpendicular to all these vectors b1, b2, b3 all the way up to bn. All of these vectors are perpendicular to E, which means E is perpendicular to the column space of A, which is S, which means E is inside the null space of the matrix A, right? Sorry, AT, A transpose. So we can write A transpose E is equal to 0, because E reside inside the null space of A transpose. In other words, E reside inside the left null space of A. Once we have got that established, let's look at P. What is P? P is the projection vector, projected vector, right? P reside inside S, which means P can be expressed using these columns, these basis vectors. Okay, that's not what I wanted to do. Oh, sorry. Okay, so we have P is equal to some scalar C into B1, C1 into B1 plus some scalar C2 into B2, right? So in other words, we can write, please remember that A is the matrix that we created using the vectors from the basis as columns. So we have A into C1 all the way to Cn is equal to the vector P. Let's call this X. That is better. So in other words, let me write it. So we have Ax is equal to P. As P is inside the column space of A, there is some vector X for which we can write Ax is equal to P, and this is what we are trying to find. What are the scalars x1, x2? What are the scalars for which we can get this projected vector? Because we are trying to find P, right? If we get X, we already know A, we will get Ax equal to P. We can find this. All right, so A transpose E is equal to 0. We got that. We also know that P is equal to Ax. So let's write A transpose. What is E is equal to V minus P. V minus what is P? P is equal to Ax. So we have A transpose V is equal to A transpose A into X. You know what? I think I need more space. So I'm just going to bring it up here. We had A transpose V minus A transpose V minus Ax equal to 0. So let's write it here. A transpose A minus, sorry, V minus Ax is equal to 0. So if we break it up, we have A transpose V is equal to A transpose Ax is equal to 0. Now, when we were doing projection for a single vector onto another single vector, A transpose A was a single number. Now A transpose A is a matrix, and this is called the Gram matrix. The Gram matrix of A. The Gram matrix of A is A transpose A. So now this is a matrix, and I cannot just divide it. For matrix we have to do just like so we have 2 on one side of the equation, 2x equal to y. We can write x equal to y divided by 2 because 2 is a number. That's what we did when we are doing this kind of projection. But this is a matrix, we cannot just divide it. So what we can do, we can do the inverse of a matrix. So x is equal to this whole portion is going to come on the left side. So A T V, sorry, I forgot to write the inverse. A transpose A inverse, this portion went to that part, then we have A T V. All right, so this is the value of x, but we want P, right? P, what is P? P is equal to A into x. So multiply A on both sides, we get Ax here. So it is P is equal to A transpose A inverse A T V, and this is called the projection matrix. By the way, how do we know that A transpose A is invertible? We just did an inversion here. How do we know that this is invertible? There is a proof that you can find in the book. The proof is also given in the lecture note, so you can see there the lecture note prepared by MZH. You can see the proof there. Anyway, so this is called the projection matrix. So this portion, this is the projection vector, and this part is called the projection matrix. So we are multiplying the projection matrix with the vector V, and we are getting the projected vector. All right, so that was the derivation, and this is your ultimate formula. Projection matrix, projected matrix is equal to A into the inverse of the Gram matrix into A transpose V. Now we mentioned two properties. Let's get this cleared up. What is the projection matrix? Projection matrix A transpose A inverse A transpose, right? So we mentioned that P square is equal to also P. So what is P square? P square is equal to this into this. Okay, so this portion becomes identity. So we have again A, so this gets deleted. We again have P. So P square is equal to P, proved. And for projection matrix, we also can show that P is symmetric. That means if you transpose them, you are going to get P. I'm going to leaving this proof for your practice. Just write P, try to transpose it and see what happens. You will see that this holds. Anyway, so that's pretty much about projection. It's a little messy considering how I showed at the same time how I showed the formula and the thought process and everything. Tried to show the thought process, so it might have become a little messy. So if you had trouble following that, please let me know, and also please look at the textbook, because for derivations, mathematical derivations like this, it is very important to see the formal approach and formal derivations line by line. In this lecture, I was trying to explain the processes and explain each step, what we are doing and why we are doing. So it will also help you to understand the whole thing if you had if you look at the lecture note, if you look at the textbook, or there are tons of online resources available. And if you still have problems after that, please let me know. All right, thank you.